All right. Thanks a lot, everyone, for coming. The second talk today will be by Xiaoyutao Luo from Duke, and he'll talk to us about Illposedness for vortex patches of Euler and alpha-SQG equations. Xiaoyutao, the floor is yours. Thanks.
Thank you, Trevor, for the invitation. So this is this talk is based on my joint work with my mentor here at Duke, Alexander Kiselev. So the Euler part is written out and posted on arXiv, but not the alpha-SQG part. So those are subject to change. Okay, so we start the talk with the Euler part. Right? So to the Euler equation in the vorticity form. So omega is the scalar vorticity and v is the velocity. So there's a link between the vorticity and the velocity given by this Bell-Savart law. So this is a transport type equation. The velocity is given by the vorticity that it transport, and the global regularity of 2D Euler dates back to the 1970s. is classical. So, but today I will not be talking about those solutions with smooth data, not classical solutions of this. Instead, I will be focusing on a class of weak solutions. So these are called vortex patches. And essentially, it's like in the simplest case, it's a characteristic function of a smooth bounded domain. And then so the inside you have vorticity, and then the outside the vorticity is zero. Okay, so in this case, the Bell-Savart law will reduce to this form, and we have this type of weak solutions falls under the umbrella of the famous Udovich theory, which says the vorticity equation is globally well posed in the class L1 intersect L2. So because the vortex patches are localized bounded solutions, so they are unique. So actually, there are quite a few useful corollary from this Udovich theory that will be useful in the study of vortex patches. So, for instance, the velocity is now log Lipschitz. So this allows us to define uniquely the particle trajectory of the vortex patches, and by this log Lipschitz, we know this bounded domain omega t evolving with the velocity. This remains a patch. So different parts of the patch boundary cannot self-intersect, and this remains a bounded domain. And in addition, we know this patch solution is not only unique in the class of patch solution, but also unique in the class of L1 L infinity solution because of the Udovich uniqueness theory. So this theory lays a foundation for us to study the vortex patches of 2D Euler equation. But what the Udovich theory does not tell us is the regularity of the patch. So in this case, the regularity of the patch refers to that of the patch boundary, right? So if we introduce the flow map generated by the velocity v, then the unique patch solution can be written like this. So the question is, does this bounded domain, time-dependent bounded domain, preserve its initial regularity for all times or or locally in time? So that was the first question in the study of vortex patches. Right. So in the late 70s, there are numerical simulations that suggest finite singularities at the level of curvature blow up. And in the 80s, Maeda even conjectured that there are smooth initial curves such that the vortex patch, the boundary of the vortex patch become non-rectifiable with infinite lengths in finite time. So these are supported by the numerics, but later we know that in the 90s, Sherman proved that the vortex patches never blows up. As if you start with say C1 alpha data, then the patch remains C1 alpha for all time. And in particular, he also obtained double exponential bounds for quantities that relates to the smoothness of the patch boundaries, say a curvature or Sobolev norm or Helder norms of the tangent or normal vectors, those kind of things. And later, his proof was simplified by Safati and Bertozzi-Constantin, and combined with the Bertozzi's thesis, we have this following theorem, which says the 2D Euler patches are globally well posed in classical Helder space CK alpha with K bigger than or equal to 1 and alpha away from 0 and 1. Okay, so that's the classical result of global regularity for vortex patches. So our interest begin with this classical CK alpha spaces, right? So this the endpoint case integer Helder spaces are excluded from the previous theorem. So what could happen at those endpoints cases is vortex patch problems still well posed in those spaces. That's our main interest today. So there is some relevance for this kind of spaces. So C1 is the borderline for cusp or angles. So if you have a angle in the vortex patch, you put this as the initial data. And as far as I know, there's no rigorous justification of what's its short-time dynamics, even I mean locally in time. So it's believed that it's either form a logarithmic cusp instantaneously, or it spirals into a logarithmic spiral instantaneously. But there is no rigorous proof for that. And also you can consider the cusp case, right? So this is like a C1. I mean, it's the borderline for this kind of situation. Okay. So and also there could happen that where you have a C1 patch that's just C1 at the point and smooth elsewhere, then this will become form a cusp at the point of irregularity. That's also that also could happen, but we don't know. Okay, so that's the C1 interest. For C2 is because it has continuous curvature, because this is a 1D interface problem. So C2 boundary has a continuous curvature, which is kind of nice. Okay, and this CK endpoint cases also commensurate with the existing result in the non-patch setting. So that I'm going to review in the next slide. So for simplicity, let's consider the Euler in the velocity form, right? So V is the velocity and P is the pressure. And if you try to run some energy estimates, there's a formal criticality threshold, which is the Sobolev space with this amount of derivative in LP, or vorticity in this space. So these are called critical space because the Lipschitz embedding fail at this endpoint. So people call this critical. The famous Bourgain and Lee Illposedness results as the following. The Euler is actually strongly ill-posed in those critical Sobolev spaces. And what's more is that they are also ill-posed in all integer Helder spaces. So what this really means is that if you take initial data in those spaces, then there is a unique solution to the Euler. and the unique solution will leave those spaces instantaneously. So quantitatively, you have the supremum over any short time interval to be in infinity, or essential supremum. Okay, so that's the kind of the rough statement, overly simplified rough statement of the Bougain-Lee result. Okay. And also there's some independent work of Elgindy and Masamudi. They consider Euler and other models of fluids in infinity-based spaces and obtain similar Illposedness results. And Elgindy with Inji Jiang, they also have a simplified proof for the Sobolev Illposedness for 2D Euler. Okay. And lately, this kind of Illposedness result has been extended to the surface quasi-geostrophic equation, SQG. They can do similar Sobolev Illposedness and Helder Illposedness, but I'm not going to talk in details about those results because that's not the focus today. So by this Illposedness results in the smooth settings, right, we can also look at the vortex patches in Sobolev spaces. Right, well, we know by Schumann's theorem what Euler patches preserves their CK beta regularity, and we can also change the scale in this problem. Right, we can consider the scale of Sobolev spaces, WKP. So in this case, I'm just measuring the WKP regularity of the arc length parameterization of the patch boundary. Right? In the Helder scale CK beta, you could do this at the level of level set or diffeomorphism. Those will give you the equivalent definition. But in the case of Sobolev scale, we do this at the level of patch boundary, so it's intrinsic to the domain. Okay, so once you settle down this measurement of regularity, we want to ask whether similar Illposedness statements will hold in this Sobolev spaces in the patch setting. So can you have a initial patch data, which is WKP, and then the unique patch solution will propagate this WKP regularity, or it will lose this WKP regularity instantaneously. So that's the first question. And this leads us to the first main result. So if you consider the WKP at the level of two derivatives, so W2P, and we can show that the Euler patch is globally well posed away from endpoints p equal to 1 or p equal to infinity. So in the middle, they are globally well posed. This is reminiscent of this C1 beta global well posedness of the patch problem, where you can't allow the Helder index to be 0 or 1. It's also away from the endpoints, right? And essentially, the proof will break down at these two endpoints, but for different reasons. Right? For p equal to 1, it's like a lack of regularity. So when p equal to 1, you have W to 1, which is slightly better than C1. And people believe C1 is the critical regularity for the Euler patch problem. So at W to 1, we don't have enough regularity to work with. That's the reason. And the proof also breaks down at W to infinity for another reason. So in the estimates, there are some operator related to the Hilbert transform, which does not play nice. Does not play nice with L infinity based spaces, right? So that's the reason why the proof breaks down at W to infinity. And in fact, the main result shows it's actually ill-posed at C1 or W to infinity. And more precisely, we find C2 bounded domains such that the unique patch solution lose this whose curvature becomes infinite instantaneously. So you start with continuous curvature, but as soon as time is bigger than 0, the curvature becomes infinite. So it's not even W to infinity. So it's a loss from C2 to not even W to infinity. So the curvature becomes infinite for all small times. And we can also show that this kind of non-C2 patch, they become non-C2 instantaneously, but they return to C2 at exactly all integer times without being time periodic. And this is also a local construction. So you can do this on top of a smooth patch. Say you have a smooth initial data. We can just modify a little bit, do a tiny perturbation for your initial data. And then the end result is still C2, but then it will exhibit this non-C2 behavior away from all integer times. Okay. So here I'm going to talk a little bit about the proofs. So just a very broad idea of how it goes. So for the existence part, it's based on the contour equation. So you fix a parameterization of the initial patch boundary, and then you let it evolve with the flow map given by the patch solution, and integrating by parts will give you this this kind of integral differential equation like this. And it's known that this contour equation is locally well posed in C1 alpha, and also CK alpha. But today we can show that this Biot operator, the velocity field V, will form a Sobolev contraction on the space W2P with constant depending on this the geometry of the patch. So you have this type of estimates, and once you have this, you can show the W2P existence, a short-time existence. And the global existence will follow from the global C1 alpha result, namely the W2P norm does not blow up if the patch remains in C1 alpha. Okay, so there's a passage from local to global via this conditional regularity. Okay, so we are not providing a new proof of the global regularity of the patch. We just use the existing global C1 alpha result to get a global W2P result. And this equation, this solution, because it's a patch solution. So by the Udovich theorem, it's unique. So we don't need to worry about other stuff like reparameterizing the contour, give you a different patch solution. We don't have that kind of situation. And W2P corresponds to C1 alpha for a suitable alpha by the Sobolev embedding, because the patch boundary is 1D. Okay. And as I explained briefly before, the proof breaks down at p equal to 1 and p equals to infinity. Okay. And now we come to the proof for the Illposedness part. So this is based on the evolution of the curvature, right? The curvature is just it's the sign curvature. So if you have a parameterization equation floating with a velocity, let's say gamma and the v, these two here are smooth enough, and formally you can derive this curvature equation. You assume smoothness of gamma and v in space and time variable. You have this. So in this equation, ds is the arc length differentiation on the boundary. and this T and N are normal and tangent vectors on the patch boundary. Okay, so this will is the curvature equation in the smooth setting. Let's see. Okay, so for the Euler patch, we look at this curvature equation, and we know it's well posed W2P, right? So if you take so all this term makes sense as a LP functions on the right hand side, right? So because it's twice differentiable with values with derivatives in LP, so all of this makes sense. And for P large, we can show that this asymptotically it becomes like this. So there is a main term that's it's given by pi times the Hilbert transform, the periodic Hilbert transform of the curvature, plus some lower order terms, right? And this Hilbert transform comes from this guy, and there's also issues with just justifying this expansion, and that requires to take P to be large. And once P is large, you have this makes sense. Okay, so okay, and it's known that this the group generated by this Hilbert transform is it's not a bounded map from C to C, right? So because this is the explicit formula for this group generated by this Hilbert transform. So this guy, the second guy has a Hilbert transform of F, and it's you can just take there are continuous functions with unbounded Hilbert transform. So that's the trick here. And so this is this construction is completely local. So because you just need to make sure the Hilbert transform is unbounded. And once you have those ingredients, you'll see why this it becomes C2 at integer times, because the second term disappear, the sign of pi t disappear at the integer times. Okay, so some open problems following this Euler Ilposedness result is the following. So in theory, the CK for k bigger than or equal to 3 should follow, and also the well-posedness WKP should follow from the same kind of computation. But the problem with our approach is that they are kind of very geometric. So for each value of k, we need to perform a different kind of computation. So there's no universal way to generalize the argument for any integer case. That's the shortcoming of that. But we expect this to hold. Okay. And the second one is the W21 case, which is the curve with integrable curvature, and we couldn't handle this because it's the patch is very less regular than the C2 case. So this is what we couldn't do, and also the C1 case, and it's I think it's the most interesting case. So if you have a C1 initial data, and then you can show the patch boundary forms a angle or cusp instantaneously, that will imply the Ilposedness. But this is still open. But people believe this is true. That it's Ilposed. It should be Ilposed as C1, but still open. Okay. So I'm going to jump to the alpha-SQG case now. So if there's no questions or comments, I'll just go ahead. So the alpha-SQG equations, they are a family of active scalar equations generalizing the Euler and the SQG. Okay, so specifically you have the same scalar vorticity, but this time the velocity that it generates satisfy this modified Biot-Savart law, where you have a 2 plus 2 alpha in the denominator. So the velocity is less regular than the Euler case. Okay, and so when alpha is equal to 0, this is reduced to the Euler. And in our setting, when alpha equal to 1/2, it goes to the SQG case. Okay, this was proposed by Cordoba, Fontiers, Mancho, and Rodrigo in almost 20 years ago. It's proposed as a model to study the finite time singularity of the 3D Euler and also the SQG. Okay. So in this talk, we will be focused on the case strictly between 2D Euler and SQG. Okay. Let's see. Okay. So compared to Euler, there are a couple of points that we need to be worrying about. The first is the velocity is less regular. It's locally only Helder or Sobolev. So W1P or C beta is no longer log Lipschitz. And this Helder index or Sobolev interchangeability degenerates as you increase the value of alpha. Okay. And we all know Sobolev or Helder vector fields don't have unique particle trajectory. So that brings the problem to the second point, which is there's no uniqueness theory for general weak solutions for alpha-SQG. For Euler, we have the nice Udovich theory, so you don't need to worry about the uniqueness. But here we don't have that because the lack of regularity for this velocity. Okay, and also this parameter alpha introduced some other significant difficulty once you try to just do some naive extension of the Euler result. If you try to duplicate the Euler argument for the alpha-SQG settings, and you will just be doomed to fail. It will be a disaster. And so the existence of the patch solutions to alpha-SQG is highly non-trivial. In fact, the first existence result by Rodrigo in 2005 uses Nash-Moser implicit function theorem. It's and it loses derivative, and it requires C infinity patch boundary in some specific case. So this innocent parameter alpha, brings out significant challenge in the study of vortex patches. So after the work of Rodrigo, people start to investigate the well-posedness in a finite regularity setting. So specifically, you have the first Sobolev well-posedness result, which is by Gansando. He showed the H3 well-posedness for the alpha patches. So the patch boundary is a uniform H3 function. And later it was extended to the more singular case, so alpha bigger than 1/2. So it's velocity more singular than the SQG. In this case, they require more regularity of the patch boundary. And more recent works of Gansando and his collaborator pushed the well-posedness to this H2 and H2 plus settings. And so this line of research uses the so-called contour dynamics. So they are based on the following idea. So because the regularity of the velocity is worse than the Euler case, but one needs to modify the velocity to close the energy estimates. So if you change the tangential velocity of the patch boundary, it doesn't change the shape of the patch. So there is another degree of freedom. So you can find a suitable contour equation. As long as this equation holds, then the shape in theory will stay the same. So it will remains to be a alpha patch, right? So basically, this equation says the normal velocity, the normal component of the velocity is equal to that given by the Biot-Savart law. Okay, and those H3, H4, H2 result refers to the regularity of the parameterization in those Sobolev spaces. Okay. So this another degree of freedom introduce a problem, which is the uniqueness, right? So because you can modify the tangential component as you want, and in doing so, you have a new contour equation. And doing this many times, you have many different contour equations. And in theory, they should all describe the same patch dynamics for the alpha-SQG. So there's the problem of uniqueness of the contour equation or the uniqueness of the patch problem. This is a very subtle problem, and it's only resolved very recently, first by Kiselev, Yao, and Zlatish in 2017, where they work out the case between Euler and SQG for H3 patches. So the significance is that you can have many kind of contour equations, but as long as the initial data is the same, you will always have the same alpha patch solution. And also, you may have some other alpha patch solutions that's not given by the contour equation. So that's constructed by some other methods, and those has to be the same with the one that you have given by the contour equation. And for the SQG case, this by Cordova-Agazendo, they require a C2 plus regularity for the SQG case. Okay, so we can just say the following statement. With suitable regularity, the solutions of the contour equations are unique in the class of patch solution. For Euler, is in the class of Ludovic solutions. So here is in the class of patch solutions. Okay, so this set of picture is taken from the beautiful work of Driscoll and Scott. They run some numerics for the original SQG case. The initial data is a thin ellipse, and they observe this kind of a cascade of filamentation as time goes by, and you'll have this two raindrop shape where there's a kind of like a angle, and this two angle shapes resembles the previous numerics by Cordova, Fontiers, Mancho, and Rodrigo in 2005. But the focus of this Driscoll and Scott scenario was in the small thin filaments between these two drops. They observe a simultaneous blow up of the curvature and the inverse of the width. But this is just some numerical evidence, and a rigorous justification of this scenario is of course open. So this Scott and Driscoll scenario also motivate us to look at this alpha patch in other spaces. So say in the classical Helder spaces, CK beta, we know the Euler patch is well posed there. And we also know alpha-SQG equation in the smooth setting is well posed there in some suitable range of regularity, of course. So could the same be said to the alpha patches? So if you have this classical CK beta well-posedness, that will be a nice extension to the theorem of Schumann. Okay, but there's a warning sign. All the existing well-posedness result for alpha patches, they are in L2 spaces, L2 Sobolev spaces. There's no exception other than the C infinity proof by Rodrigo. So there's a warning sign here that this well-posedness may be false, and that's exactly what we prove here. So it's we almost finished this, so it's 23 plus. Hopefully we can post this soon. So for all alpha between Euler and SQG, this patch problem is strongly opposed in all the C2 Hilbert spaces. So this beta can be 0, can be 1, can be anything between 0 and 1. There's no restriction. So more specifically, we prove this statement, right? So given this alpha and beta, we can find a C2 beta bounded domain such that any alpha patch solution with this initial data will satisfy this quantitative statement. And so the definition of a alpha patch will be introduced in the next slide. I have been quite vague about this, but it will be on the next slide momentarily. So the definition that we adapt is the Eulerian definition. So if you have a bounded domain with some regularity, we say it's an alpha patch if the characteristic function solves the alpha-SQG equation. This is a very weak definition compared to the Euler case, because in the Euler case you have the log Lipschitzness of the velocity, so you will expect the usual correspondence between the Lagrangian definition and the Eulerian definition. But in the case of Sobolev vector field, those correspondence may not always be true. So, but this is nevertheless the definition we had in. So if you have any patch solution in this in the sense of this definition with the initial data that I picked, this patch will satisfy the bound that I had. So again, as before, the regularity of the patch refers to that of the boundary, which we measure by this arc length parameterization, and they are all equivalent up to a translation. So there's no ambiguity. And the reason we state the theorem in this hypothetical term is because there's no written down C2 beta uniqueness for alpha patches, but they are expected to be unique given by the C2 plus uniqueness of Cordoba, and Sandel for SQG. So C2 beta for alpha patch, for alpha smaller than SQG, should be unique. Okay, and the next result concerns the same Illposedness problem, but in the scale of Sobolev spaces. And in contrast to Euler, the alpha patch is strongly opposed in all non-L2 Sobolev spaces in a suitable range of regularity. So you take any p not equal to 2, and immediately this 2 minus 1 over 2p, it's bigger than 0. So there is some non-empty sets of alpha there, because you can also take p equal to 1. That's fine, but not quite 1, but just something close to 1. And for all this alpha, it's strongly opposed in this W2p space, in the sense that on the previous slide. Okay, so there's a drastic change from alpha equal to 0, the Euler case, to alpha bigger than 0. Because Euler patches are well posed in non-endpoint Hilbert spaces and non-endpoint Sobolev spaces. But here for alpha patches, they are basically opposed everywhere, except when p is equal to 2. And the restriction of alpha less than this exponent in the Sobolev case relates to the existence of the flow. If you take p is less p to be less than 2, then there's no even existence result for alpha patch, and hence the hypothetical tone of the theorem. So any W2 patch with this initial data has to be ill-posed. So this is independent of the uniqueness theorem. So no matter what kind of patch you have, they have to be ill-posed. They don't exist. Okay, and both ill-posedness proof in the Helder and the Sobolev case, they break down for SQG. So when alpha is equal to 1, there are many places that the proof will break down. First of all, the velocity is not even bounded, and the continuity of the velocity is a crucial ingredient in the proof. And also the driving mechanism is a kind of dispersion in the equation, and that vanishes as alpha goes to 1/2. So we can't quite do that. Okay, so here I'll just briefly touch upon the proof of those ill-posedness results. So the proof is by contradiction, because it includes a region where even the existence is not known. Okay, so you assume the existence of such a patch with the initial data that you designed, and in the sense of the Eulerian definition that I had, then we first establish the well-posedness of the Lagrangian trajectory of the patch boundary. Namely that if you have a regular enough patch, the trajectory of the patch boundary is unique. It exists and unique and satisfies some regularity. But we are not claiming the patch solution itself is unique. We just say the trajectory generated by each patch is unique. And with the Lagrange flow established, you can analyze the leading order dynamics of the curvature evolution, similar to the Euler case. But in the Euler case, this is a part of the existence result. So that's a lot easier. In the alpha-SQG case, we will see this severe loss of derivative that leads to many kinds of difficulties. So this is the second step. And once you have the leading order dynamics, you can show the ill-posedness of the curvature equation. The leading order dynamics will be some kind of dispersion in the curvature equation. Okay, so the first part is to show the well-posedness of the Lagrangian flow of the patch boundary. So you given a patch, and then we look at the parameterization of the patch boundary, then you solve this equation. So we define the solution by bundling up each trajectory into a flow map, and we show this flow map it's C1 plus, and this plus goes to 0 depending on all sorts of parameters. So there's a severe loss of derivative, right? You start with W2P or C2 beta, you just end up with C1. And that's not to say the patch, it's not, I mean, it's ill-posed. It's just say that the trajectory subjected to this equation is only C1. So this does not imply the ill-posedness. In fact, it's the enemy. So it makes it even harder to show ill-posedness. But nevertheless, because it's C1 plus, you can define diffeomorphism and define curvature, right? So this parameterization it's only C1, but we assume the patch boundary is W2P. So this diffeomorphism allows us to define the curvature in the Lagrangian variable. So in other words, the irregularity of the parameterization only appears in the arc length metric of this parameterization. The tangent, the normal, they all satisfy the expected regularity. Once you can define the curvature flow of the patch boundary, you can look at the the curvature equation in the smooth setting. And of course, in this case, this equation does not hold classically, and some kinds of distributional argument is needed, right? So we have to couple the arc length. So this G here is equal to the magnitude of the derivative of the parameterization, right? The metric. So the metric and the curvature together, they will satisfy this leading order equation. Again, this also holds in the sense of distribution, because K is not, I mean, curvature kappa is not does not have enough regularity to satisfy this. So all of this is at the level of some kind of distributional sense, and also for this lower order terms. So the leading order operator there, it's this Hilbert transform composed with a fractional Laplacian. So in the Euler case, it's just fractional Laplacian. And what's worse than the Euler case is that you have a mysterious factor here. So it's not exactly linear. So it is kind of no way to compute the group generated by this linear term, because it's multiplicative perturbation of this guy. And for this, the linear term is already quite complicated. So there are several difficulties related to this model. And this, as I said, the lower order terms are not even functions. They just don't lose that much derivative compared to this alpha. So for alpha, this alpha loses 2 derivatives, roughly speaking. So the lower order terms just lose less than 2 alpha. They still lose derivatives. So all of this makes sense at the level of distributional sense. So to prove the Illposedness in the distributional sense, we consider the following model, right? So we replace this kappa G equation by this F equation. The F bar inside is some variant of F. Let's just say F bar is bounded in some suitable spaces that you are considering, okay? And the capital F is a distributional forcing. By a solution of this equation, we of course mean this distributional formulation for any test functions, smooth test functions. And for this, I think it's also compactly supported in time. Okay, so you set up this model, and we prove under some technical conditions that roughly says the forcing is of lower order, and the F bar is continuous in the space that you are considering. Then this equation is imposed in all the non-L2 spaces. So Sobolev, or I mean LP, Lebesgue or Held. So this is what we prove, and so this is based on perturbative arguments. So because when the F bar is not F bar, it's just F itself, this we know it's opposed. This is by the classical result of Wenger in the 60s. Right? He built a specific function in LP for p less than 2, such that the evolution of F leave LP instantaneously, and moreover you have this estimates for each little Paley pieces of this function. So this delta Q here, it's the little Paley projection at frequency 2 to the power 2 to the Q. Okay, and this blows up in this format. There's a epsilon loss there, but that's not very important to our discussion. Okay, so Wenger's example shows the original linear equation without the bar is Illposed in all the non-L2 spaces. And we're trying to extend this to this F bar setting under suitable continuity conditions on F bar. Okay, and then also Wenger's example only works for p less than 2. And in p less than 2 case, you can take f to be the initial data. You take this f to be the initial data, and it will work. For p bigger than 2, you can't take this as the initial data. Some kind of duality argument is needed, so you need to take the LP dual of this, and you add them all up as the initial data. And either way, we can show that use this little prelude decomposition. We can show that in the weak formulation, you still have this instantaneous blow up of the LP norm when p is not equal to 2. Okay, so that's more or less what's going on in the Euler-Posedness proof. So putting them all together, right? So we need a bounded domain whose curvature is given by the bad part and the good part, because Wenger's result it just gives you a LP data, right? You don't know whether there exists a bounded domain with this curvature, right? Because curvature is kind of more geometric. Not every function is the curvature of something. So there's arc length in play, and also the arc length integral of the curvature has to be 2 pi. Those kind of things. Even they are even if the average is 2 pi, they could still mismatch. So you need to take care of that. But we nevertheless we show that there are bounded domain whose curvature is given by Wenger's function plus a smooth part, the good part, the smooth part. So that will be our initial data. And if the patch exists, then the curvature exists, solves the curvature equation in the weak sense with this initial data. And it satisfies the model. We have to verify the curvature equation, satisfy all the technical conditions in the model equation. And then you apply the Euler-Posedness result for the model equation to get the Euler-Posedness of the curvature equation and close the argument. So the curvature cannot be in the corresponding space for this W2P or C2 beta patch, and you get a contradiction. So it has to be opposed. Okay, so finally, as I said, there are a few open questions, right? So C1 Euler case, we don't know whether this develop an angle, a cusp, or a spiral even, we don't know. And also the SQG case breakdown. And if you just forget about the existence part, just pretend everything goes through, you have the curvature equation, whatever that even means. Then the Fourier multiplier of this group generated by the this leading order dynamics looks like this, and that gives you some kind of translation in the physical side. So there's no degenerate dispersion. So the proof breaks down. So you could conjecture that the SQG patch is well posed in those W2P C2 beta spaces. We don't know. Another interesting remark is to consider the Dirichlet-Scott scenario in this curvature arc length formulation, because they show this simultaneous blow up of the curvature and the inverse of width. So we can try to consider this scenario in this formulation. And because this curvature arc length formulation, it has modular the translation and rotation. So what's left in the equation is just the shape, and hopefully that's useful. But I don't know. Okay, so that's all I want to talk today, and thank you all for your attention.